Today's topic is a mishmash of things that all kind of relate to the same topic, and that is ultimately the idea of atomic orbitals. Now, for some evidence of this, what we need to look at is we need to look at the idea of magnetism. So we all know that some elements are magnetic and others aren't, right? So you put a magnet on something like iron and it works great. You put a magnet on some other metals and it doesn't work so good, right? So scientists decided to test a variety of different of these elements and see which ones responded best to the magnetic field. So here's what they do. They take a tube, and if you take that tube and you put the sample in there, and then you put that sample in between an electromagnet that provides a magnetic field, you're either going to get a response or not. And if you get a response, right, then it is going to show up on this scale. You're going to see some sort of a response. There's some action on a scale or some sort of a device there. And I don't want to get specifics into the numbers of everything, so we're going to use a tremendously scientific scale where I'm going to use arrows. And if the arrows are off to the left like this, then that means there is no response to the magnetic field. If, however, it goes all the way over here to the right-hand side and you see an arrow way over here to the right, then that means there's lots of response to a magnetic field. And then obviously in between there's going to be more and more. So if it's here, that means there's some. If there's here, it's some more, and here there's even some more, right? This is very little. This is lots, but maybe not the most. So we're just going to use it because it's really not important, the specific amounts of it. We're just going to use this as a vehicle to learn a little bit of something about what's going on inside the atom. So let's take a look now at the fourth row all the way across. If you get out your periodic table and take a look at it and start here at potassium, all we're doing is we are looking at the magnetic responses of all of these different elements as you go entirely across all 18 elements that are in that fourth row starting at potassium. And at first glance, it just looks like a bunch of mishmash of arrows, and it doesn't even really look like there is a pattern here. A couple of things about this, a couple of terms that might come up for you in problems and on the AP test and so forth. The first of which is diamagnetic. If they say something about it being diamagnetic, diamagnetic is just this. There is no response whatsoever to a magnetic field. So this one and this one alone is diamagnetic. Excuse me. If it is instead paramagnetic, here, that means there is a response to the magnetic field, to a magnetic field. So that would be anything from here all the way over here would be paramagnetic, with obviously this being the most paramagnetic, something like this being slightly paramagnetic. So you've got results from slightly all the way over here to lots and lots. So taking a look at these guys, for example, if we start here, we can see that potassium is slightly paramagnetic, but calcium apparently is completely diamagnetic. And then if we go across the row, we've got more and more magnetism, a little more, lots, and then a little less, and a little less, and a little less, and a little less, until finally we are all the way back down here at 0 again. But we're not done, because apparently for some reason it goes up and up and up, and then down and down, and then finally all the way to here we've got none again. So it doesn't look like there's any pattern here really, except it kind of goes up and then back down again. Excuse me, coughing today. And but it turns out that if you know a little bit about the periodic table, and you know a little bit about electrons in an atom making a magnetic field, you can actually glean a great deal of information from this that is going to be tremendously useful for us for predicting properties of these substances. But let's take a moment and talk a little bit about those magnetic fields. Now, if you remember from your physics days, if you have a charged particle spinning around something like a nucleus, it's going to create a magnetic field because of things like the right-hand rule and all that kind of stuff. And again, I'm not really interested in any of that. If you are, take a physics class, and I'm sorry for you. But what we're interested in really is just the idea of there either is a magnetic field or there isn't a magnetic field. Where do these ideas of diamagnetic and paramagnetic come from? Well, paramagnetic would be some electrons spinning in a magnetic field, making a field, making that magnetic field one way or the other. So again, if this one here is spinning in a particular way, then that means it's going to create a magnetic field either from north to south or south to north. Again, there's a whole rule about that in physics, and I'm not really concerned about that. So there is an electron that is apparently spinning in a particular direction, and it is making a magnetic field. Now, what would be diamagnetic? Well, you can't have electrons that spin, but then don't make a field, but what you can have is what's called destructive interference, which is where the electron spins one way and makes a field, we'll say north to south. But then if you have in the same area an electron that happens to be spinning the other direction, well, that one is going to make a field from south to north. And if those guys are in the same area as each other, then what you're going to have is you are going to have a field that is going north to south and a field that is going south to north, and those fields are going to cancel each other out, which is why this guy here would be diamagnetic. So diamagnetic is when you have two electrons that are spinning in opposite directions and their fields cancel each other out. A paramagnetic is one where you have electrons that are only spinning in one direction and they all help each other, or there is one that is by itself. All right, so now let's once again take a look at this pattern here. Now, there's a lot going on here, so let's just focus in, if we could, on the row that we are looking at here, and let's start simple. So remember that when these shells break into subshells, there's all of these different overlaps that occur. We talked about this in the last discussion here, where you got 1s, 2s, 2p, 3s, 3p, and so forth and so on, all the way up to there. We're going to focus in on just the calcium all the way over across to the krypton, which means that we are going to be focusing just on the 4s, the 3d, and the 4p, which is what these elements are in. The 4s, the 3d, and the 4p. So let's start at the beginning, and let's start over here with potassium and calcium. So here is your 4s. Now, the first one is, we're just going to have to pick. Right? We're just going to have to pick an electron. It doesn't even really matter which way that you put it, because potassium, being the very first element in this valence shell, only has one valence electron. So here's potassium. We've got one valence electron. Now, we could pick up or down, doesn't matter, but typically speaking, you just start with up, and we're just going to go with that. All right. So we're just going to say that we're going to start with potassium having an electron going up. Well, that is now paramagnetic, which makes sense, because if you have paramagnetic, that means you have an electron that is spinning, and there is nothing to cancel it out, because again, there's only that one electron, so there's nothing to cancel it out. So that makes sense. But now let's look at the next one. What about calcium here? Calcium, there are two electrons that we have to do. Now, we have a couple of choices, I suppose. Let's see where the evidence takes us. We could, I suppose, do this. Do an electron up and another electron going up. But if they are both spinning the same direction, then what will happen is both of their magnetic fields will be going from north to south or south to north, but they're both doing the same thing, and if they're both doing the same thing, then they don't cancel each other out. So if that's the case, then we should see a larger response to the magnetic field, and in fact we don't. We see no response to the magnetic field. So this guy here is back to diamagnetic, no response, none, zero, nada, nix, niente. So that can't be how it goes together. Nor could we put it like this. Well, what if we just started with it down? If we had down and then down, well, that's going to be the same thing, because that's going to be an electron spinning in one direction, creating a magnetic field, let's say it's south to north, and then another electron spinning in the same direction, again, we'll say south to north here, and if those two are doing the same thing, then they constructively help each other, and that's not what is occurring here. So what must be occurring is that one of those electrons is spinning up, and one of those electrons is spinning down, and now what we have is the circumstance that we see here, which is the diamagnetic, and in a diamagnetic situation, you have one electron that is spinning one direction, and one electron that is spinning the other direction. And if that is the case, then they cancel each other out, and you end up with a diamagnetic situation going on here. So that would make sense in the S subshell that is here. There is the S subshell, that for potassium you're going to put one up, and then for calcium you're going to put one up and then one down, which is why you get a little bit of response here and then no response here. So that then leads us to kind of a global pattern. And what scientists have called this is, they have called this an orbital. And an orbital is basically a sub-subshell. So we've gone shell, subshell, and instead of calling it a sub-subshell, they call it an orbital. And in an orbital, you can have two electrons, and one of those electrons can be spinning up, and one of those electrons can be spinning down. You cannot have them both up. That is against the rules. Nor can you have them both be spinning down. That is apparently against the rules. And all of this is outlined in what's called the Pauli exclusion principle, which says that no two electrons in the same atom can have the exact same four quantum numbers. But at this point, we're getting pretty darn deep into the specifics. We're getting deep into the weeds of the quantum mechanical physics of everything, and it's really kind of beyond what the AP test is going to ask you. So all you really need to know is that in any sub-subshell, which is an orbital, you can fit two electrons. So you can fit two electrons, and one of them has to be spin up and one of them has to be spin down. And they usually represent an orbital by a box. And the box just shows you the location of those electrons, one spin up and one spin